For those who have never witnessed the process of basic steel making, get ready for some pretty dynamic views from Whg Pittsburgh Steel Corporation. It's an awesome operation in terms of size, yet highly intricate in the pinpoint coordination of people, materials, and processes. For all its overwhelming magnitude, the process of steel making can be likened to a stringently choreographed ballet, where every step of the dancers must be in sync. We are pleased to give you an inside look at exactly how we make steel happen every day.
Hello, and thanks for joining us again on another employee video. We all work in the steel industry. We all work for the same company, but we don't all get a chance to see exactly how steel is made and understand the process. That's because we're a company that's spread out all over the country. Take a look at this map and just see how many locations we have. First, our Wheeling Pittsburgh steel sites. Next, our Wheeling corrugating and Unimass division locations. As you can clearly see, we are spread out across the entire country. The steel making process begins with what we call the primary operations. These primary operations are comprised of 3 plant sites in Follinsby, West Virginia, in Steubenville, Ohio, and in Mingo Junction, Ohio. And they are intertwined. They rely heavily upon each other to produce steel. Let's get started with the first stop on our tour, Follinsby, West Virginia.
Ever since iron masters in the 18th century learned how to make coke, coal has been a critical ingredient in iron and steel making, and there is certainly a lot of coal near this river. In fact, for more than 100 years, this spot on the Ohio has been used for iron making. The coke batteries are on the West Virginia side of the river at Follinsby. Of course, the coke ovens in our 4 massive coke batteries are a bit larger than back then. Special mixtures of high-grade metallurgical coal are loaded into the chambers called coke ovens. Heated in the absence of air, the coal becomes coke, which is almost all carbon. This is a process called destructive distillation. Consider that if the coal was heated with air present, it would become ash and be of little value to Wheeling Pittsburgh Steel. There are byproducts too, which we use in many ways. Coke gas heats the coke ovens and provides basic fuel for the other operations around the steel plant. Other byproducts are sold to chemical companies and end up as everything from cleaning fluids to pharmaceuticals.
Hi, I'm Stan Roston, hourly foreman, coke plant, Follinsby, West Virginia. The iron and steel making process begins right here. We receive metallurgical coal. It's barged to us up the Ohio River from southern West Virginia. That is basically the start of our coke making process. We take 3 different blends of coal, metallurgical coal, mix it, and bake it in our coke ovens. This coke is then used for the making of the steel on the Ohio side of the river. Once the coal is mixed and transferred via conveyor belts to coal bunkers, machines deposit the coal in the ovens. The coal is basically baked at approximately 2100 degrees. This process develops your carbon coke once the coal is in the oven for approximately 17.5 hours. The oven is now ready to be pushed. To accomplish this, a door machine operator pulls a coke side door off and spots his coke guide up on the oven in question to be pushed. A pusher machine and an operator pulls the same identical door and lines up to push this oven. Communications between the operators is essential. The oven is then pushed into the quench car and taken to the quencher where water is then deposited on the coke to cool it. This coke is then transferred via conveyor belts to railroad cars, which is shipped to the blast furnaces on the Ohio site.
Automated trains bring the coke to the blast furnaces. It is here that the raw materials are melted down, refined into iron. Men still must prepare the pathways to take the iron in one direction, the slag or waste products in another. There are numerous examples of Wheeling Pittsburgh Steel's ongoing commitment to maintaining modern facilities. For instance, the rebuilding of the No. 5 blast furnace at the Southworks, a $54 million effort, was a massive undertaking. The investment significantly increased the furnace's iron-making capacity, ensured that the molten iron's quality is among the best in the industry, and provided additional safeguards to further protect the environment.
Hi, I'm Bob Baker. Welcome to No. 5 Blast Furnace in Mingo Junction, Ohio. The coke that you saw earlier is transported to the blast furnace by railroad car. We use coke as a fuel, and it is charged into the furnace. The coke is charged into the furnace right along with the iron pellets, and we use scrap, and we use flux, and it's all measured out and charged into the furnace. And as it comes down through the furnace, it's melted, and we tap it out of the bottom of the furnace. We separate slag from the iron because basically the slag is the impurities of making iron. We separate it so we have pure iron because that's what the BOF needs. If we send too much slag down there, then it makes their job harder to separate the iron and the slag. The iron and slag are separated in our trough. We have a block of refractory in the middle that we call a skimmer. The iron goes underneath of it because it is heavier, and the slag is basically just skimmed off the top and goes in the other directions into the slag pot. An iron bottle is a brick-lined torpedo ladle. That's what we put the iron in. It's lined with brick, and the iron in that bottle is transported to the BOF. The slag pots are cast iron pots, and they look like thimbles. And once they are full, they are transported to the slag dump where they are dumped out. Well, that concludes our tour of No. 5 Blast Furnace. I hope you better understand the iron making that we do here. Now let's head down to the BOF, the basic oxygen furnace.
Think of the BOF as a lot like Mom making a cake from scratch. Flour, butter, and other ingredients go into the mixing bowl. Well, you get the idea. Here, the mixing bowl is a gigantic furnace capable of holding 300 tons. And what we mix are iron, scrap steel, lime, lots of oxygen, and a variety of other alloys. We add the ingredients to the furnace in a process we call charging. We call the mixture itself a heat. The charge consists basically of about 250 tons of iron and 90 to 100 tons of scrap because steel is a recyclable material, yielding 293 tons of liquid steel. Think of it this way. An automobile may have 1 ton of steel in it. That means that every 55 minutes, Wheeling Pittsburgh is making the equivalent, steel-wise, of about 300 automobiles. The process takes about 19 minutes. What makes it all happen in just 19 minutes is the oxygen used to refine the iron into steel. The oxygen is introduced through a water-cooled lance about a foot in diameter. Nearly 22,000 cubic feet of oxygen a minute are used. The fluxing materials are loaded in from overhead bins after the oxygen blow begins. During this period, the temperature rises to 3,000 degrees as the refining takes place. The fumes are drawn off and cleaned through Venturi scrubbers to reach acceptable environmental levels. During the melting or blowing process, the impurities from the iron are burned off and transmitted into the slag and waste gases. This refining process takes about 20 minutes. Then the furnace is rotated so that the heat of the steel can be tested for temperature and chemistry. If all is satisfactory, we will tap the heat and send it to the continuous caster.
I'm Sonny Capers. This is a basic oxygen furnace, the BOF for short, in Mingo Junction, Ohio, and I'm the operator. Once the heat is finished being tapped, we run it out so the crane can pick it up. It takes it to a station which we call the CASO-B, which is a new station we've just put in. They take it down there and they test the steel and make sure the chemistry is what we need. Well, once they get it to the CASO-B and the tester run, then they proceed to make it exactly to the specifications of the customer. From the CASO-B or trim station, the heat is taken a short distance to the caster, and that will be our next stop.
The continuous caster takes our 293 tons of 3,000 degree Fahrenheit liquid steel and turns it into a solid slab of steel in one smooth, non-stop motion. A problem that had baffled steelmakers for 100 years. It's the incredible temperature, of course, which makes this such a complicated process. Imagine the special materials we need to use in all of this equipment so it doesn't melt down. We call the insulating material refractories, and there's a lot of it here. The steel goes straight down into the molds that begin to create steel slabs. The molds are water-cooled. This brings the temperature on the surface of the steel down, low enough to make it harden into a shell. More than 10,000 liters of water per minute are used to do this. Of course, the inside of the strand is still molten. The molds force the steel to make a 90-degree turn. By this point, the steel is about 1,500 degrees in temperature. Computers monitor every aspect of this operation.
On this display here, it shows the mold. That's the upper part. It has the different segments in the machine itself. And this is a graphic display of what's going on outside and in the machine. It tells me the casting speed. It tells me how many tons are in a tundish. It tells me the temperature of the water going inside the mold versus the temperature going out of the mold. And if there's an alarm, it will turn red and an alarm will come off on our panel. And I have to make the necessary adjustments, notify the right people, depending on the severity of the alarm.
Close monitoring of the process is a must. The temperatures put severe pressure on the equipment. For example, the refractories lining the tundish are 12 inches thick. The steel slabs are glowing cherry red as they leave the mold and head down the runout area. There is careful control of temperature and roller support to ensure the precision of the slab. The high quality of caster slabs makes for better rolling. The process doesn't stop, not even to cut the slabs into manageable lengths. See how the cutting torches are on tracks, synchronized exactly with the speed of the caster? And because slabs vary in metallurgical specifications, each must be numbered so it can be tracked and sent ultimately as sheet steel to a customer. The continuous caster makes better steel slabs than any other method. The caster here at Whg Pittsburgh Steel is capable of casting 2.3 million tons of steel a year. Slabs that are more uniform in metallurgy and more uniform and exact in their dimensional specifications. More importantly, think of the caster as a closed loop approach. Because very little air touches the steel as it goes through the caster, there are fewer impurities in the steel. The mold system reduces subsurface defects. The outer surface is cleaner and smoother. It's the kind of steel that puts a smile on the faces of the employees in the rolling mill. We describe the BOF as being a lot like Mom's cake mix. Think of the strip mill as Mom's pie crust. Of course, it's a little more difficult to squeeze a steel slab into a 1/8 inch thick strip than it is to get that apple pie crust just right. The steel slabs are reheated in what looks like a giant oven. Then they start a journey through the 80-inch hot strip mill. The first part of the trip is called the roughing mill. The slabs then enter the coil box. After the coil box, it's delivered to the finishing mill and then sent down to the down coilers. A hot strip coil box processes this 2,000 degree, 1-inch thick transfer bar into a coil form for temperature conservation and equalization. Next, the steel is uncoiled to the finishing mill at an even temperature profile, which helps achieve the temperature and thickness control needed for the customer's order. Hot rolling operations such as this must maintain control of the actual work roll temperature, and we do that by water. We apply water with high-pressure sprays to keep the rolls cool in this rolling process. In just 5 roughing stands, the steel is reduced from 9 inches to just under 1 inch. The slab travels in a straight line nearly a mile long, squeezed and pushed and shaped every inch of the way. As it gets thinner, it gets longer, and it goes faster and faster until it looks like a blur. And along the way, the coil box, hydraulic AGC, and a very precise computer system work to control temperature, width, and thickness.
I'm Carl Panetta, the speed operator in the 80-inch mill. As with everywhere else at Whg Pittsburgh Steel Corporation, we take great pride in trying to produce a quality product for our customers. The customer is the boss in Whg Pittsburgh Steel. A few short years ago, we had a $47 million renovation of the 80-inch here at the finishing mill. Employees were very much involved. As a matter of fact, they had a team effort with the coil box and developed several teams that give a tremendous amount of input to it. As you can see with our screens, those are all employee developed. All the computers and things like this, everybody had input to them. What they wanted, where they were placed, is all by the Whg Pittsburgh Steel operators. They asked employees what they wanted, they told them what they wanted, and the company tried to meet it if it was right.
Well, I hope you enjoyed your tour. Pretty impressive, isn't it? I also hope that you've learned something new about your company today. Next time, we intend to bring you the finishing operations, where you can see what happens to the steel after it leaves Mingo Junction, Ohio. Thanks again for joining us, and we'll see you next time.